Hello, this is the fifth video in a playlist I call Generalized Linear Models, and here we're going to look at the general structure for generalized linear models. In the previous four videos we mainly focused on the canonical link, but this is for any link function. And I have background videos 1 through 4 is my playlist of generalized linear models. BV5, derivatives of the inverse trig functions. BV6 is a weighted least squares regression, Mahalanobis distance. And here we assume that the distribution of y follows an over dispersed exponential family. And the over dispersion comes into play with this parameter phi, which we're going to let it be, phi divided by w. And where w is a known weight, and actually the over dispersion we're going to assume is known too. And for more details of this, you can look at BV1. The linear predictor we're going to call eta, and it's for a particular individual, so eta I, they have a linear combination of covariates and betas. The link function. So we're going to let mu I be the expected value of yi, and g is going to be smooth and invertible. Smooth means it has derivatives and it's continuous and nice properties there. Then g of the mean is going to equal to eta I. So that's going to be our linear combination. And g is what's called the link function. And in the previous videos, that when we took the link function of our mean, we got the canonical parameter back, and then we let it be the linear combination of the x's and betas. But here it does not have to equal the canonical parameter, so it's just a general link function. It has to be invertible, so we can take the inverse of both sides and get this. So mu I is the inverse of our link function evaluated eta I. But remember, eta I is just the linear combination. In BV1, the mean, it was equal to the first derivative of the log partition evaluated at our canonical parameter. Note that g is partly chosen to extend the range of the means to the real number line. So, for example, if we're in the normal distribution setting, our y is normally distributed, so it takes on values of the real line, and so does the mean. And so when we use the identity link to map the reals to the reals, it makes sense. When we're in the Poisson regression setting, our data are non-negative, and the mean of a Poisson is non-negative, so we need to find a function that takes those non-negative values to the real number line. Same way with the binomial distribution. Our data are 0, 1 variables, but the mean can take on any value between 0 and 1. So we need a link function that maps the 0 through 1 interval to the real number line. And so that's partly what the link function does. The variance of y, which we noted in BV1, is the second derivative of the log partition times this dispersion function, which is the phi over the w. Well, this right here they let be what's called a variance function. I think in a previous video I'm like, I wonder why they called the variance when the variance is everything. Well, that's because it's the variance in our exponential family, and then the dispersion parameter is just a multiplicative constant of that. Now it makes sense that this is a function of our mean, because the mean can be back solved for mu. So theta I is here, but the log partition is invertible, or the first derivative of it is, so we can write theta I in terms of mu I and put it in here, and then we get functions in terms of mu I. And that's actually one of the assumptions about using generalized link functions, that the variance of our data is actually a function of the mean. The likelihood as in previous videos, is the product of the individual likelihoods, are all independent, which becomes this. The log likelihood is you take the log of this, and so the exponential function goes away, and we just get what's in the exponent. Now note that we're gonna think about this as the sum of Li. So each one of these is Li, and then we're summing it, and then that's how we get the log likelihood. Because we're going to deal with Li when we're taking partial derivatives and derivatives, and which is just this part, or this technically, but that drops out. And so then we sum it later, and it just makes it easier when we focus on one Li. Now, we want to maximize this distribution in terms of betas, right? So that's our goal. We're creating a linear combination of betas that have covariance in front of it, and we want to maximize this likelihood. But there are no betas here, right? It's all in terms of theta I and phi and the data. Now, I've seen some videos where they go in and they rewrite all this to make it in terms of beta, and then you maximize it. And that's just fine. This is kind of the way I was taught it and the way my brain thinks, and so you're going to get this. So we're going to have to take this in terms, if we want this in terms of the betas, then we're going to have to use a chain rule a few times, and you'll see what I'm saying in a bit. So we're going to start taking partials of things that we know, and it'll all come together in the end. So here, since it's partial, we have theta involved, so let's just take the partial derivative with respect to theta I. And so we get y, and that's just the derivative, and the constant has to come along. And this right here is the mean, the derivative of the log partition. So we get this. We can take the derivative with respect to eta I. Remember, that's the linear combination. So then when we want the jth beta, so then it's just the variable in front, xij. Then we know that mu I is the derivative of the log partition. And so if we take the derivative of mu I with respect to theta I, it's just the second derivative, which is what we're calling the variance function. But notice that we proved in BV2 that the derivative of the log partition is a strictly increasing function, so it's invertible. So if we want to find the derivative of theta I with respect to mu I, we can actually take the reciprocal like this, because it creates an inverse function. This might be easier to see when I do it for step 4 for another function. But then this we determined was the variance function. So the derivative of this is this. And really details can be sought out in BV5 for taking derivatives of inverse functions. Now this one's a little more explicit. So we have the length function of our mean is our linear combination, eta I. And then you can take the inverse of it and back solve for mu I, right? So when we take, the derivatives of inverse functions kind of have a unique property here. So the derivative of eta I with respect to mu I is just the g prime. And then to take this, it looks like the reciprocal of that. That's just 1 over the derivative of this, which we determined was the first derivative of the length function evaluated mu I. So we get this. And again, see BV5 for more details on taking derivatives of inverse functions. Now, let's look at the score functions. Now, the score functions are essentially just the derivatives of our log likelihood, with respect to the parameters of interest. And here we're interested in the beta parameters. So we're going to take the derivative of our log likelihood with respect to beta. Now, the first one here is easy because our log likelihood is in terms of theta. So it makes sense to take that. And then this one here, the linear combination, the eta is the linear combination of beta. So taking the derivative with respect to beta, this is easy. And then so somehow you have to think of, you have to connect the dots from this one to this one. And so, if you do it this way, then this chain ends up just being this right here, which is what we wanted. And we took the partial derivatives of all these on page 2, and if you just put them together, that's what it is. Now, in many cases, this is written over this piece because it looks, you'll see in a second, and then these are written usually under this one. And so the score, now remember, so this is just a partial with respect to one of those ni's, but we want it to the sum. So if this is the score of the jth beta, right? So then the sum comes into it of this. So, this is it's 100% this, but we have to take the sum. So that's where we get the jth score. Now, sometimes this is rewritten in a different form, and I'll show you in a second. So this bottom piece is actually this. So sometimes they put the partial here and the xi, but then this combined can be thought of as this piece, which is the partial mu I with respect to beta I. So sometimes they put that in place of here. But either, all three are the same, and you set it to 0 and you solve. Now remember, this is just for one beta. So the score function, we have to take derivatives with respect to each of those betas, and we go from beta 0 to beta p. So there's p plus 1 equations here that we're solving. Now let's find the observed Fisher information. Now the observed is the partial, the two partial derivatives, it's a matrix. It becomes a matrix. And then the Fisher information is actually the expected value of the observed Fisher information. So here we are going to calculate it for one of them. Now, normally, so that's like the, 1 Li. But normally there would be an in here, and it means there's a sum going on. But we'll just do it for one, and then we're going to do it for the jkth element of this matrix, which is this. Then the partial with respect to k is, don't forget the minus out front, times this, but we calculated that up here. So let's plug in what we know. And now I'm going to call this step star, because taking the partial of this with respect to k, beta k, then we'll have to use the multiplication rule. This times the derivative of this plus the derivative of this times that. But then this beta, there's no betas in here, so we're going to have to use some sort of chain rule. And this is it. So here we have, it's in terms of mu I. So the first one, this is what we want. With respect to mu I makes sense because there's only mu i's. And the last one, it makes sense because it's a linear combination. We want beta, right? So that we get the beta here. But then what can we put in the middle that creates this product rule? So those cancel, and we get this back. So we need to find each of these partial derivatives. And that's what we'll do in the next few steps. And then, so here we'll do the first one, and then so this is with respect to mu I of this, which is this up here. So then you get this. So it's the it's right here. So we use the quotient rule, so it's the bottom times the derivative of the top, and it's minus 1, and then minus the top times the derivative of the second, and since that's constant, it's just the derivative, and then it's squared on bottom. So there's an AI that can be factored out and canceled with one of those, and then so what's left over, so we have a minus, and then there's a minus, so I take the minus out front, and we're left with this over that, and this piece over that. Notice the AI was factored out. So that's the partial derivative with respect to mu I. So the partial of mu I with respect to eta I is 1 over the derivative of the link function evaluated mu I. We did this on page 2, I think. Here is the derivative of eta with respect to beta k. And so it's the kth piece here, so it's going to be the ikth element. The partial of this with respect to beta k. We have to daisy chain them, right? Because this is in terms of mu I, so let's take it in respect to mu I first, and then eta I and k, so then we get this chain rule. But we just calculated each of those pieces. So this was this, well, this when you calculate it is this. This we calculated, this we calculated. Remember, use the chain rule of this. So it's the, you know, take that to the top times the derivative of this with respect to mu I, which is 0. Then it's minus this times the derivative of that, which is how we get this, all over squared. And those we calculated. So now I went straight to calculating what we wanted to. But there's a couple pieces in here that I'm like, oh, I didn't do those. So I just wrote them down. So I'm going to skip to 6 below and come back to this. So 6, if we look at the partial of this function with respect to k, you know, and this is in terms of mu, so we take a mu first, and then we use the chain rule to get to the bk, which we want. And then this is, in each of these we calculated before. And this will come into play up here, actually right here. That's how we go from here to here, is through this formula. And then this one, the partial mu I with respect to beta, mu's are in terms of etas, so we do a chain rule here, and this piece is this, that is this, and then the product. So now when we're back to this, remember, so this is for one of the LIs, and then it's the partial twice. Oh, so there probably should be a 2 right there, which I forgot. And so now we take the derivative of the first, the first times the derivative of the second piece plus the derivative of the first times the second. So we had to use the multiplication rule here. But now all the pieces fit in, and I'm going fast. The video is a little bit long, but you can rewind it, or, you know, and then replay it. This gets carried down to here. This piece, remember, it was the chain rule, so it was the product of these, right? It was down here, and we got this. So this is the first, that's the second, and that's the third piece in the chain rule. Then the plus. The partial of this respect to beta k is this, and then this piece just comes down. Now in here there's a xi jk the same, there's an xk, there's 2 of these, so we'll have to leave one of those behind. There's an ai both, there's one of these variance functions, so all those are factored out here. And I left them in pieces like this instead of writing them as one fraction. So here, so that's factored out. This is factored out. There's one left here, and this is a plus. So I'm going to take one of those and write it over that, and that's where we get the 1. And then this over this is that. And then there's a minus there. Don't forget that. And here the minuses cancel. So we're left with one of these. Both of those go away, but we're left with one of these, and that's where we get this. And this is the observed Fisher information. And I leave it like this because on the next page we're going to take the Fisher information matrix, which is the expected value of this. And these are constants, constant. This is constant, but this is a constant. So when it's the expected value of yi, which is just a mean, so this actually goes to 0. And the expected value of this, these are constant, that's a constant. Expected value of yi is mu I, and that goes to 0. So 0, 0, 1, and 1 times this, you just get this. So the Fisher information matrix is going to be just that piece right there. So now, when we look at this, so the Fisher information matrix of n, our sample size n, we're going to just find the jkth element of this matrix. And that means we have to take the observed Fisher information for our sample, an N. Remember, we just looked at one of those. So when we looked at just one, we got this piece. But since it's over sample N, we have to sum it, and that's where that sum comes in. Now, sometimes this piece is put in the back, and it's written like this. So, and this is a daisy chain of two things. So the mu I with respect to eta I and the partial of eta I with respect to beta I, you get these two components. But some people like to write it like this, which sort of emphasizes that we're taking the partial derivatives with respect to beta I and beta K. It sort of makes that more explicit, but I also think some people do it just because it makes it look more complicated. I don't know. But I always work with this function. But you'll see this one a lot in books, right? So this piece is this, and that piece, when taken to the back, is this, and then this you can write it in partial derivatives. So this is the Fisher information. Now let's find it in matrix notation. Now, if I can do nothing for the statistical community except for make people say, hey, are they using numerator notation or denominator notation, I actually think I've helped out the statistical community. Now, it seems like, I'm going to say the majority of what we do, we just use numerator notation, but not always. And it seems like when we maximize the multivariate normal, we always use denominator notation. So in my video, when I maximize the multivariate normal, I use numerator notation, and I actually got some comments saying, hey, this does, it's not right, or it's not correct, your transpose is wrong. And that's because I use numerator notation, and usually they use denominator notation. So anyway, so I think we need to always make sure when we're taking derivatives of partials of vectors and matrices, explain which notation we're using. So here's the score function, and remember that the score is it's a vector of all the partial derivatives, right? So this is a vector, and you can think of it as the score of beta 0 here, and then beta 1, beta 2, beta partial with respect to beta p. And so since this is a row vector, I put a transpose because I like it in terms of column vectors. So now this right here is this. Now notice that this is a scalar and this is a vector. Now in numerator notation, this actually becomes a row vector. So we have to transpose it to get it back to a column vector. And then when we sum all these are are constants, and they're just multiplied by each component. But that's why that transpose is there. Now if we were to use denominator notation, we wouldn't need that transpose because a scalar, and then with a vector below, that ends up being a column vector. And then this right here, remember that is this, but it's really x is over something. X is over something. And so this you can think of as x, and then that denominator gets shoved into this this diagonal matrix, and then these are just vectors. And anyway, this becomes this vector product. Now the Fisher information matrix in matrix form is this, where W is this diagonal matrix. So you can think of it, this is an X, and then that in the back is an X, and then we have a bunch of stuff in the middle, and that's what this is. So this is the Fisher information matrix in matrix form. Now iteratively reweighted least squares, and you can look at BV4 where we did iteratively reweighted least squares regression for the canonical link function. This is for the general link function. And so there's two pieces here. Understanding what we're doing for iteratively reweighted least squares, that's one. And two is, how does that connect with maximizing the likelihood function? So we're first going to address the iteratively reweighted least squares piece of that. So, try to understand what's going on there, and then later we'll show that that is equivalent to maximizing the likelihood function. So if we let Z be the linear combination plus this. So yi minus mu I gi. So notice this can be thought, this is, so in matrix form, this would be x times beta. And then we could think of this times epsilon because this is a vector. And it has a mean of 0, but it has a variance. So we're going to have to use weighted least squares somehow. So the mean of this is just the linear combination. And the variance of the zi's, this is constant, goes away. This comes out squared, the variance of this. That's constant, so it goes away. The variance of this is this. So it's our variance function times our over dispersion function. So step 1 in the iteratively reweighted least squares piece is we need to estimate mu I. And then we're going to let that be yi. And actually, I really think it would be helpful to look at BV4 also with this video, because I say things a little bit differently, but which may make sense more in one versus the other. And now, once we know mu I, we can take the link of it, and then we can estimate what our linear combination is, right? And that's without having to know the x's and betas. We can just kind of estimate it. Now, remember our zi was this. So instead of eta, I just put our linear combination. So our first estimate of yi, so if we put yi here, that's 0. So this goes away for our first estimate. And then we're just left with this, but that's estimated by the link of our data, right? So that's the first estimate. And this right here will make more sense when we get to step 3. But you can back solve this for mu I. So and we'll come back to that. But for step 1, we don't need it. But we could, but this is just yi, right? Right, so if this is our linear combination of eta, which is g of mu I, so if we put g inverse of g of mu I, but we're letting mu I be y, so it's just y, so it's 0. So I mean, it doesn't hurt to think about it now, but anyway. So now once we know the z's, then we can plug it into this vector. So this is the ith component, so we have to do this for each component. And the weight vectors are in terms of mu I, right? But we have an estimate for mu I. It's just the first iteration is yi. So we put that, so now everything is known on this side, and we come up with an estimate of beta. And then once we have an estimate of beta, we put it back into step 2. So we're going to repeat steps 2 and 3 until convergence. So we put this beta back in here, get an estimate, plug it in here. We already have our estimate for beta. Then all these mu i's can be used to update our weight vector. Then we come up with a new beta. And then boom, boom, it's just a back and forth until these get really, really close to each other, which we call convergence. And then we're done. So now you ask, how's this equivalent to maximizing the likelihood? So if you look at BV6, where I talk about the weighted least squares regression, this is the solution to a system of equations. And that system of equations is this. This is what's called the normal equations. So solving this, you come up with an estimate of beta, okay? But z, let's plug in what we know about z, which is this piece right here in matrix notation. So it's x beta, g is this diagonal matrix. So then notice that when we multiply this into both pieces, then this are equal. So we subtract it from both sides, so we get 0, and then we just get this times this piece right here. But now this is a vector, so let's think about the ith component of this. So it's the ith component, which implies, and then if you just look at the ith component, this row, which is actually the ith column in the original data matrix, times this diagonal. Well, this is diagonal and this is diagonal, so it's a diagonal, and then you multiply it times this vector, you get this back. Now notice one of those cancels here. But then we can just multiply that to the other side, and we're left with this. So this comes down, These two pieces we just write as an inverse, right? This and this are gone, and that comes down. Well, this is the equation that we want to solve. So we set this to 0, right? And we solve it. And that's maximizing the log likelihood. So here we're maximizing this is equivalent to this, which is equivalent to this, which is equivalent to this, which is equivalent to this, and the solution of this is weighted least squares regression. And we're done. Well, that's all I have for today. I hope you enjoyed that. I sure did. Please like the video, so you don't miss the next one. I plan on maybe 5, 6, 7 more videos in the area of generalized linear models. So thanks a lot. Bye.